This is section 5.4, the fundamental theorem of calculus. This theorem is probably used more than any other theorem on all of the AP tests, on both the FRQ and the multiple choice. So make sure you understand this. Make sure that all the little details make sense to you. Before we get to the fundamental theorem, we're going to do a little reviewing. So this function here, a of x, it's called an area function. So basically, we're starting at -1 and going to some value of x that we choose, and we want the net area of the function. And this f is another area function, but we're starting at 5 instead of -1. So I'll work out the first couple, and then you can pause and work out the rest. So the first one, we want a of 3. So that means we want the integral from -1 to 3 of our function. What's the net area from here to here? Well, as I sweep this way, since it's below the x-axis, it's going to be negative. That's just going to be -27. And then for f of 3, we're going to take the integral, but we're starting at 5 and going to 3 of our function here. So we're starting at 5 and going backwards to 3. Well, normally the area would be 3 and it's on top, it'd be positive. But we learned if we go backwards, it's opposite. So that's going to be -3. All right, go ahead and pause and try to do the last 4 of these and then come back and see how you did. All right, so welcome back. This one, we're taking the integral from -1 to 5 of our function. Well, -1 is here and 5 is here. And so this is going to be a negative net area, -27. That's going to be +3. So that's going to be -27 plus 3, or -24. All right, f, that should be a capital F. I don't know what happened. F of 5 is going to be integral from 5 to x, but our x is 5, so that's going to be 5 of our function. But the area from 5 to 5 clearly is 0 because you're starting and ending at the same place. All right, this next one, you're starting at -1, ending at 9 of our function. And so we want the area from here all the way to 9. So it's going to be -27 plus 3 minus 35. Because this is below, so it's minus. That's below, so it's minus. That's above, so it's plus. And what does that get us? -24, -59, I think. I hope I'm adding right. 30, 50, 62 minus 3. I believe that's right. And then the last one will be the integral. And we're starting at 5 on f because they told us. And we're ending at 9. So this will be from here to here, which will be -35 because it's below the x-axis. All right, so a little bit of reviewing, and now we're going to move on to the fundamental theorem of calculus. So what is this saying? This, you need to let your brain get wrapped around it. We're going to do some examples and make some big connections from the last section. So you have a continuous function and the antiderivative of f on a and b, so you have both of those. Then, check this out. This you learned yesterday was the net area. So the net area is going to be that. What is that? This is the antiderivative evaluated at the upper limit minus the antiderivative value at the lower limit. Now this is just notation we use. This just means plug in b, then plug in a, and then subtract. So it's the same thing as this. It's just a short way of writing it. Now, I don't think you grasp how crazy that is and how powerful that is. And you will see as we move on. It's important that you start making connections with that. I'm going to write this another way. Instead of writing it like this, I'm going to write like that. And so if you have f prime from a to b, the net area of that is going to be the original function at b minus the original function at a. So it's the exact same thing, because this is the antiderivative of that. How do you know? The derivative of that must equal that. Well, the derivative of that is that, so it makes sense. This will be more significant as we do more examples. Let's start with example 2a here. We're going to evaluate this using the fundamental theorem that we just found. So the first step for this is we need to find the antiderivative. So the rule, I add 1 to the exponent, which will become x squared, and then I divide by that. So I'm going to take that 1, add 1 to get 2, but then you divide by that. And then we get minus 6, it's a constant. And then to this 3, I'm going to add 1, so it's going to be cubed. I'm going to divide by that, and I'm going to go from 0 to 10. That's this notation here. And you have to make sure you know what that means. So this, wow, is 30x squared minus 2x cubed, 0 to 10. What does that mean? I plug in 10 first. 3 times, wow, 30 times 10 squared minus 2 times 10 cubed. I plug that in first. Then I plug in 0. 30 times 0 squared minus 2 times 0 cubed. So I plug in the top one, I get that. I plug in the bottom one, I get that, and I subtract. That's what this is saying. I take my antiderivative, plug in the top number. I take my antiderivative, plug in the bottom number, and subtract that. And it's this format. So if I were to do this, that's 100, that's 3,000 minus 2,000 minus 0, and I get 1,000 for my answer. So the net area, okay, what does that mean? So this is the graph of this function, 60x minus 6x squared. That's a parabola. We know it's a parabola, and it's upside down because of minus. This is the graph of it. But in other words, the area of this region is going to be 1,000 square units. That's the meaning using the fundamental theorem. Crazy, eh? So that's the answer to part A, question 2A. So I don't know if that amazes you, but the fact that if you take the antiderivative, then you plug in the b and you plug in a and subtract, that gives you the net area. I don't know. To me, that's pretty wild, pretty crazy, right? How does that happen? What does the antiderivative have to do with the net area? But that's what the fundamental theorem says. Okay, another example. Excuse me. Okay. Same thing. We're just going to find the antiderivative of 3 sine x dx from 0 to 2 pi. Now, remember the rule, if there's a constant, I could pull it out in front. I'm just going to apply that right now. We actually did that in the last problem. We just didn't show it. Okay, the derivative of what is sine? And you might say, copy the constant, cosine x. But if you take derivative of cosine, it's minus sine, because the derivative of that must be that. So to make it match, you need a minus in front, and 0 to 2 pi. And then the same rule. We plug in the upper one first, minus 3 cosine of 2 pi, minus, we plug in the bottom, but cosine of 2 pi is 1, and cosine of 0 is 1. So we have negative 3 plus 3, 0. How's that possible? Well, what does this function look like? It is a sine wave, right? With the amplitude of 3. Well, the net area, that area, is equal to that area because it's symmetrical. And so therefore, that area cancels out that area for a net area of 0. And what's interesting is the area of that is 3, and the area of that's 3. Just kind of weird that the area under a sine function of each hump is just 3. If the amplitude was 1, it would just be 1. No, just kind of a interesting little thing there. All right, one more example. Take a look at this one. So we're going to rewrite this. Now this is t to the 1/2 over t minus 1 over t. I split it into two separate somethings. My brain's not working. Terms, that's the word. And I rewrote square root of t as t to the 1/2. And then the next step, the rule is you subtract these exponents. And there's a 1 there, you don't see it. 1/2 minus 1 is negative 1/2. And then the antiderivative of 1 over t is ln of t. Whoa, Yoshida. If I take the antiderivative, I don't need that. I've taken the antiderivative. And that's going to be from 1/16 to 1/4. All right, let's continue going here. The rule says I plug in the upper number first. So that's going to be, well, actually, let me rewrite this. That negative moves it to the bottom. So it's 1 over, and 1/2 power is square root. So I'm going to rewrite like that. I like that much better. Now let's plug in the top one. We get that in ln of 1/4. Then I subtract and I plug in the bottom value. And there's actually some stuff we can do to this to simplify it. This is going to be 1/2. You flip it, it's going to be 2. And the square root of that is 1/4, but you multiply by the reciprocal, so that's going to be 4. Now, if you pop this into your calculator, you get a value about negative 0.886 as your answer. A couple of other fun little things we could do. ln of 1/4 is ln of 4 to the negative 1 power. And I can do the same thing. This is ln of 16 to the negative 1 power. And then we can p in front of the log. This actually becomes 2 plus ln of 4 minus 4, and p in front of that log, that negative comes in front, plus ln of 16. These all would still get you the same answer, but just practicing the rules of logs. Now, what does this mean? The net area from 1/16 to 1/4 of that curve is going to be negative 0.866. Yeah, and that makes sense. Here's the graph. There's negative 1/16. There's 1/8. It's got to be negative because it's underneath. And so the area of that little piece is going to be 0.886. All right? So those are examples of the fundamental theorem. We can find net area by using the fundamental theorem. We find the antiderivative, plug in the top number, plug in the bottom, then subtract. We're going to do some applications of this, and it's going to be very, very significant. We got another example here that we're going to do, example 3. So we have the graph given to us of this. The region R1 is bounded by the curve and the x-axis, so it's that and the x. And R2 is the curve and the x. They want us to find the net area of the region. Okay, I can do that. But to make my life much easier, I'm going to multiply this out. This will be x squared minus x minus 2. If I just multiply these out, I'll get that. And then I'm going to distribute the 6x to that. So that's going to be 6x cubed minus 6x squared minus 12x. That's going to be a lot easier to work with. So I'm going to integrate 6x cubed minus 6x squared minus 12x dx. And I'm going to go from negative 1 to 2 because we learned this gives us net area. And we learned how to solve that using fundamental. We're told find the antiderivative, which I add 1 to the exponent and divide by that. So it's going to be 6x to the 4th over 4. I add 1 to that and divide by that. So it's going to be a 3 over 3. And I add 1 to the 1 there. You don't see that there's a 1, so it's going to be 2. And I'm going from negative 1 to 2. I can simplify this a tad bit. This will reduce to 3x to the 4th over 2 minus 2x cubed minus 6x squared from negative 1 to 2. So now I'm going to plug in 2 first. 3 times 2 to the 4th over 2 minus 2 times 2 cubed minus 6 times 2 squared minus, then I'm going to plug in negative 1, and I'm out of room here. So it's going to be 3 times negative 1 to the 4th over 2 minus 2 times negative 1 cubed minus 6 times negative 1 squared. And if you do that on your calculator, you actually get a number. Now, you could leave your answer like that if this were an FRQ. This simplifies to negative 27 over 2. It makes sense it's negative because that's bigger than that. So there's more area below, so it's going to be negative. So that's the answer. Now, let's read this question. Find the area of the region bounded by the curve in the x-axis negative 1, 2. What's the difference? This is net area. Net area means the area of that minus the area below. But if you want the area, not net, you have to take that and you have to add that. You have to combine those because areas are not negative. So if they want the area of the green and the area of the pink, you got to find that value and make them positive and add them up. So let's do this. How do you find that? Well, there's 2 possible ways to do this. What I'm going to do, I'm going to take this and I'm going to copy it and paste it because I need that. So let me copy and paste. But here's what we're going to do. I'm going to stop at 0. And then I'm going to take this again. I'm going to copy and paste that. But here's what I'm going to do. I'm going to go from, let me talk a little bit here. I'm going to go from 0 to 2. So what I've done, I've taken this 0 to 1. And then this part's going to be negative, right? So 0 to 2 is going to be negative. But to make a negative positive, I'm going to subtract that. So I'm going to take this, which come out negative, and then when I subtract it, it's going to make it positive. Okay? Well, we're going to get the same antiderivative. We're going to get that, or this. So I guess I'll just copy and paste that. And some of the details of how this is going to work, I'm not going to do everything. I'll explain what I mean by that. So this equals, and I'm going from -1 to 0, minus, and then we're going to copy and paste this again. And this one's going to go from 0 to 2. Now, I'm not going to plug everything in for you, but you'd plug in 0 here, here, and here. Then you'd plug in -1 here, here, and here, and you would subtract that. You get one blob minus another blob. Minus, then you do the same thing. You'd plug in 2 here, here, and here, and you'd get a blob. Then you'd plug in 0 here, here, and here, and you get another blob. And so you just combine those, and subtract those. After doing all that work, you will get an answer of something 17 or 18 and a half. That's what you're going to get. So that is going to be the area of the regions. So it's going to be this area plus that area. But how would I write that? So what's going on here? It's actually the integral from -1 to 2. But to make this positive, how do I make it go on top? I do the absolute value. So this is how I could write if I want to. Equals 18 and 1/2. So this is equivalent to this. Because what does the absolute value do? It takes something negative and makes it positive by taking the opposite of it. So this is the notation you could write that represents that. Okay? So if you want the total area, you would absolute value. And you might ask, well, how does that help me? I still need to integrate two separate regions. But if we're doing calculator work, you could just pop that in your calculator and you would get that answer. So that's where it becomes nice. Okay, so that's basically fundamental theorem, but still you do not understand how powerful that is. We're going to do a bunch of examples to have that make sense to you. All right, there's another fundamental theorem of calculus, another version. So if you have some function, and very important to note, a on the bottom, that's any constant. A is any constant. And the x on top, you got to notice is your variable x. There's your variable. And here you have t's. That is different from that. They're not the same. Because this is the bound of your definite integral. You're going from a to x. X is going to be some constant. You might pick 5. It'll be from a to 5. This t is your variable of your function. It's going to vary. So this is not the same as that. Just important to note. And here is what the theorem says. If you take the derivative of this, or in other words, the derivative of that, all you do is plug x in for t. Bam. Now, why is that? Well, think about this. The derivative and the integral are inverse functions. So if you're taking the integral and then you take the derivative of that, they're going to kind of cancel each other out, kind of, sort of. But it only works if this is any constant and that x matches your variable. So you're taking the derivative with respect to x. That's got to be an x. You just plug x in there and you're done. I don't know why, but every year people struggle with this. You need to wrestle with this and have it make sense. You have to know this is a constant. We'll do some examples. And that has to be just x, like that. So, just like any other derivative, you have to have a variable. There it is. There's your variable. As silly as it seems, like if we have d dx of sine x, that's going to be cosine x. There's my variable x. And I know just to take the derivative. Well, there's the variable x. I know just to plug it in. Now, if this were x squared, all of a sudden you couldn't do this, and you'd have to use chain rule. So be aware of that. What would that be? Chain rule, what's the sine of box? It's going to be cosine of box, and then you have to multiply by the derivative of the box. So you have to use chain rule when that is not match up with the x. And we're going to see that happen here very shortly. So I will do an example A, and then you can pause and do B. Check out what's happening. And I wanted to do a different form, and I forgot to put it in. Oh, well, I might just change it on one of these just so we're comfortable with it. Because I want to see you use both. I want you to see both forms. So our variable is x, there it is. And that is a constant matching a constant x. And this says the answer is you should place x in for t. So this will be sine squared of x, and that's our answer. That's it. We've done it. Okay, go ahead and pause and do B. Okay, welcome back. Let's see if this matches. We're taking the derivative. Variable's x, that's x, so we're happy. There's our 2 pi, that's a constant, that's x. All we do is plug in x for t. So our answer here will be e to the sine of x squared minus 1, done. That is the answer according to the fundamental theorem of calculus, the other version. Let's keep going. Letter C. How do we do that? Does that match our fundamental theorem? You can pause and try this on your own if you want. Well, the bottom has to be a constant. Uh-oh, that's not a constant. I'm in trouble because I can't use this theorem. But I learned something. I learned it at some point. I learned that I can switch these. But if I do switch them, it becomes minus. I learned that. Now I'm almost done. I have it in the form I want. There's a constant. That x matches that x. All I do is plug in x there. But the negative, don't forget the negative here. I could have brought that in front of the derivative. And then I plug in x in for t. So I'm going to get ln of x squared. Done. There's my answer. Okay, we are just cranking along here. Everything's making sense. This one I'm going to change the formatting of this just so we are used to this. I'm going to make this white. I'm going to cover this. And I'm just going to call this f of x equals No, I'm not going to do it in this one. I'm going to do it on the next one. There's a reason why I'm not going to do it yet. Okay, let's take a look at this. That's x. That's x squared. Oh no, it doesn't match the theorem. Since it's not x and x squared, that becomes box. We have to use chain rule. So we plug in box. That's what we do. We always plug in x, right? Plug in x for t. Well, I'm still going to plug in box for t. So this will be ln of x squared squared. I just replaced t with that. But then you always have to multiply by the derivative of box. So my answer is 2x ln of x to the fourth. There is letter D. Be careful about the chain rule. All right, try letter E. Go ahead and pause and then try this on your own. All right, welcome back. Let's take a look at this one. So we're good because we have a constant, and that x doesn't, oh, that's not x. Therefore, it's going to be chain rule. This is box. So the rule says I plug in box for t. I can do that. So it's going to be sine x cubed minus sine x. But I have to multiply by the derivative of the box. Derivative of sine is cos x. Bam! There is the answer for E. All right, for F, I have a problem again. That's not a constant. So what do I do? Because this requires a constant. So I learned a rule. I can rewrite, and this is where I'll rewrite this. I'll call this a of x equals. I can split this up from x to any number. Pick a number. 5 sounds good. ln t squared dt plus the integral from 5 to x squared of ln of t squared dt. This is a property that we had in the last section. I can break any integral up into 2 separate integrals as long as I start at the same place, I end at the same place, and these are the same numbers. That was from the last lesson. Okay? That is another common thing that appears on the AP test, so be comfortable with that. Now, I'm almost perfect. This one almost matches, but I need a constant in the bottom and x on top. Guess what I'm going to do? I'm going to flip those. So I'm going to get 5 on the bottom, x on top, ln of t squared dt. And the second, oh, what happens when I switch those? I need to put a minus in front. And the other one is fine, so I'm just going to copy and paste this. I'm going to run out of room, I can just tell. Yeah. I'm going to put it down there. And so, yeah, it's just this plus that. Now they want the derivative, right? So I'm going to say the derivative, and our variable is x, so it's dx. That's x, so it matches up, so we just plug that in there. So it's going to be minus ln of x squared. That's the first part. Here's the crazy part. We have a problem. That's not x, it's x squared. So that's going to be box. We're going to plug box in there. So that's going to be ln of box squared, but we need to multiply by the derivative of the box, which is 2x. So here's our final answer. Minus ln of x squared plus 2x ln of x to the fourth. And if you want to switch them around to get the positive one first, that's no problem. We can do that. But there's our answer to letter F. So there's a lot of properties and rules that we need to practice a lot to get used to. All right. We're going to bring this all together, everything we've done for the integration section and doing some things from the previous sections. But you're going to have some light bulb moments, hopefully. This stuff's kind of crazy. Some of your brains might twist a little bit, but you might want to watch this video a couple times before we take the Chapter 5 test. On a certain workday, the rate in tons per hour which unprocessed gravel arrives at a gravel processing plant is modeled by this. That is the rate at which unprocessed gravel arrives. So visually, you have trucks full of gravel. There's piles of dirt or gravel, rocks. And they're arriving at a processing plant. And so you have a hill of rocks that they're piling onto that. Okay? So you have things arriving. This is the rate of arrival. Okay? That's what it says. You got to read what it says. It says the rate in tons per hour of arrival. So that's what G is. I'll write that down. So rate of arrival, and that's G of T. And then what else do we have? And we're gonna talk about this. Is measured in hours at the beginning of the workday when I'll do this somewhere else. When t equals 0, beginning of the workday, there's already 500 tons. Okay, so I'm going to put A. I know I'm all over the place. A sub t is the amount of unprocessed gravel. So basically, how big is your pile of gravel? When t equals 0, the amount of gravel is already, there's telling you, 500 tons. It's 500 before the day begins. There's already a mountain of gravel. Okay? And the rate at which it's arriving is G of T. I'll get more significant impact about that. But then we read, during the hours of operation, didn't want to do that. During the hours of operation, the plant processes gravel at a constant rate of 100 tons per hour. So they're taking this pile of gravel and they're processing it. I don't know if they're cleaning it, they're doing something. So they're taking away. So the truck's bringing stuff and then gravel's being taken away. And how fast is being taken away? It's going to be at a rate of 100 tons per hour. Okay? So I'm going to call that removal. Rate of removal. I'm going to call that R of T for removing, and that equals 100 tons per hour. Okay? The unit tons per hour on both of those. I have a lot of stuff going on here. Yeah, let's keep going here. Now the question. Find G prime at 5. Using correct units, interpret the meaning in the context of this problem. So part A, G prime at 5, which is dg dt at t equals 5. So you just can plug that in your calculator and get an answer. So if you put this in your calculator, this is a calculator problem. If you put this in your calculator, you would get an approximately negative 24.588. You have to round it off. And we'll talk about that. So that would be your answer. Now let's think about what this represents. G is the rate of arrival. Its derivative is negative. That means G is decreasing. You learned that from chapter 4. If G, the derivative, is negative, then G must be decreasing. But what's G? The rate of arrival. So the conclusion is the rate of arrival is doing what? Is decreasing. Okay? At the rate of 24.588, and they wanted units. I'll talk about where the units come from, but it's going to be tons per hour squared when, that's not a when t equals 5. Now, how do we get all that? So, back again, don't overthink this. The derivative of g is negative. That means g is decreasing. But what is g? G is the rate of arrival. So the rate of arrival is decreasing. Well, how fast? At this rate, because g prime is a rate. So at the rate of 27.58 tons per hour when t is 5. All that fits in. But how do we get the units? Okay, g prime is the change in g over change in time. Well, g is measured in tons per hour, and dt is measured in hours. Well, that's your unit, tons per hour, which converts tons per hour squared if you multiply by the reciprocal of that. So that's part A. Okay, that's kind of a review of chapter 4. But now we're doing B, the total amount of unprocessed gravel that arrives at the plant during the hours of operation on this workday. What? Okay, this is the fundamental theorem of calculus. Why is this fundamental theorem? Okay, I will explain to you on B. Find the total amount of unprocessed gravel that arrives at the plant during hours of operation. Okay, why is this fundamental theorem? I'm going to integrate g of t dt from 0 to 8. And how is that going to be the amount of gravel? Okay, I will explain here. What's g of t? G of t is the rate of arrival. How fast gravel's arriving. And it's in tons per hour. Okay? That's what g of t is. What's dt? dt is the amount of time. And that's going to be hours. The unit's going to be hours. So this is how fast gravel's arriving. Say it's 50 tons per hour. How much gravel will arrive in 1 hour? 50 tons. Because every hour is 50 tons per hour, and it's 1 hour. So if you multiply a rate of arrival times the time, that tells you how much gravel has arrived. But what does integration do? If you remember from the last section, it multiplies the height times the width and adds up all those rectangles. So integration is really multiplying. You're multiplying these two. This is a rate of arrival times the amount of time. So how fast gravel's arriving times the time that's arriving gives you the amount of gravel that's arriving. And so that actually gives you the amount of gravel that's arrived. Let your head get wrapped around that. If you integrate a rate of arrival, it tells you how much has arrived. And let me tie that to the fundamental theorem of calculus, the first one. Huge. If you integrate f prime, it tells you how much f has changed. Okay? Think about that. If you're going to integrate f prime, it gives you the change in f. Okay, think about that. And we're going to go back to this problem. And this is huge that you make this connection. G is the rate of arrival. It's the rate of arrival. So if you integrate, which is the derivative of arrival, if you integrate the derivative of arrival, it gives you the change in the amount that has arrived. Okay, back to this. Hopefully this sinks into your brain. If you integrate the derivative of something, it gives you change in what it's the derivative of. So let's go back. This is huge. This is like awesome. If you integrate G, which is the rate of arrival, it gives you the change in the amount arrived. Okay, I don't know if that sunk in, but you need to process and get that to sink in because it's huge. You will see this all over the AP test. Now this you would actually put in your calculator, and if you put this in your calculator, you would get about 825.551 tons of gravel. Okay? Now, I'm not going to do part C. I'm not going to do part D right now. Those are actually chapter 4 things. So I'm going to move on because this video is getting long already. More powerful stuff. Next example. Crazy stuff. Okay. So we have a function f given right here. That's f. And they define a function g. G is this. It's like an area function. It's the net area from 1 to x of this function f. Okay, so we want g of 2. You should be able to do that because we just had some example problems like that. G of 2 is 1 to 2 of f of t dt. 1 to 2 is from there to there. What's the integral from 1 to 2 of this function? It's the net area. Well, let's figure this out. What's the slope of this? What's the rise and run? Well, I go down 1 over 2, right? So that's 1, 2, that's 1/2. The slope is 1/2, right? So looking at this is 1, from there to there is 1, and then that is going to be 1/2. And so this is going to be the net area. It's going to be negative base, which is 1, times the height, which is 1/2, and it's a triangle, so it's 1/2 base times height. So it's negative 1/4 will be the net area, or g of 2. Now g of negative 2 is going to be integral from 1 to negative 2 of f of t dt, because it's from 1 to x, and x is negative 2. So this time, we're going to be going the other direction. And where's negative 2? Right here. So it's going to be this and this. But we're going backwards. So when you go backwards, it's opposite. Normally you subtract that. This time we're going to add that because we're going backwards. So that is a half a circle. The area of a circle is pi r squared, but it's only the bottom half, so we will divide that by 2. Okay? And then this is a triangle. So the area of a triangle is 1/2 base times height, but since we're going backwards, it's going to be minus 1/2 base times height. The base, this is 1, and the height is 3. So it's going to be 1 times 3, and there's our answer. You don't have to simplify it. That's part A. We're going to do part B. Part C, I don't think we're going to do today. because that again is related to chapter 4. I just want to focus on chapter 5. So that's A, part B. So it says for each of g prime at negative 3, g double prime at negative 3, find the value or state that it doesn't exist. So how do I find the derivative of g? G, I don't know. Or do I? Well, here's g. What's the derivative? Remember that fundamental theorem? If that's a constant and that x matches your variable, all you do is plug in x for t. So that's going to be f of x. That is g prime. Crazy, huh? So if that's the case, what's going to be g prime at negative 3? Well, it's going to just be f at negative 3. But what's f at negative 3? Let me erase this real quick. We can do that. Negative 1, that's negative 3. It's going to be the y value right there. Well, this slope is from over 2 up 2, so the slope's 1. So if this is negative 4, if I move over 1, I go up 1, that's going to be 2. So that answer is going to be 2, using fundamental theorem by taking the derivative of an integral from a constant to x. Now check this out. What's g double prime going to be? Well, I'm just going to take the derivative of that. That's going to be f prime of x. Pretty cool, eh? Well, let's do this. What's the derivative of f? Well, I'm on what g double prime at negative 3 it's asking for. That's f prime at negative 3. What's the derivative right here? It's the slope of the tangent line. It's 1. So the answer to that is 1. I am done with B. Okay, it's going to get better than this. It's going to get better. Here we go. This is where it gets crazy. Important concepts are being learned here. All right, we are told some stuff. A particle moves along the x-axis, so it's left and right. Here is the velocity of the particle. And at x equals 2, it starts at 0. So what does that mean? That means x sub 0 equals negative 2. That's going to be very significant. Okay? So the question is, when is a particle moving to the left? Okay, a particle is moving left if the velocity is negative, right? So I'm not going to do this part. This is not really chapter 5, but I'll explain. You would graph this function here on your calculator, and you're going to get a cosine function. So it's going to be a cosine, which is going to look something like this. It's going to wind on down, right? So you want to know when the moving to the left. We're going to look for when the velocity is negative. That's when it's moving to the left. So you find that time and that time on your calculator, and you got when it's moving to the left. So that's what you can do part A. But that's not the part I really want. I want B. Find an expression that gives a total distance traveled by the particle. Total distance traveled. So let's look at B. How do I find the distance traveled? I'm not looking for displacement. So let me explain. If I integrated v of t from 0 to 12, actually it's a 6, right? 0 to 6, that would be displacement. I can put that in my calculator and find that, meaning where do I end up compared to where I started? So look at this graph. You would take that area, subtract that area, and I don't know how many ups and dips and doodles we have, but basically I would take the area on the above part minus the area on the bottom, but I don't even have to do that. The calculator does that for you here. So it moves right, then it moves left, then it moves right. And so to find, for part B, the total distance, that will not do it, because this integral will subtract that, and we want this distance plus that distance plus that distance. We want to add them all up. So how do we do that? Here is something you have to know. Total distance. Wouldn't it be awesome if I could take this negative velocity and move it up top and make it positive? If I can move it up top, then when I integrate, I add those up and get the total distance. Well, I can do that. It's 0 to 6 absolute value of v of t dt. This gives me the total distance traveled because it takes any negative velocity and makes it positive, therefore adding all the distances up instead of subtracting. Okay, so that's B. Part C, find the acceleration of the particle at time t. So acceleration, this is something you learned last chapter. It's the derivative of velocity. So you would take the derivative of this, but it's cosine of box. What's the derivative of cosine of box? Minus sine of box times the derivative of box, which should just be pi over 6. That is the acceleration for the particle at time t. Now, is the speed of the particle increasing, decreasing, or neither at times t equals 4? So how do you do this? If you don't remember, you would have to find the velocity at 4 and the acceleration at 4. So you would do this in your calculator. If those two are both positive, then the speed is increasing. If they're both negative, the speed is increasing. If they're opposite, then the speed is decreasing. So that's what you would do for that. That again is review. I want to get to part D because part D is huge. Part D is used all the time on the chapter 5 test. I know this is a long video, but this is hugely important. Part D, they want x at 4, right? They want the position at 4. I want to remind you we have x at 0. So I'm going to write that down here. We know at time t equals 0, the position is negative 2. Now here's why this is huge. Watch very closely. This is fundamental theorem. We learned this. If I take the derivative of x and integrate from 0 to 4, what does that equal? Well, I take the antiderivative of x prime. What is that? That's going to be x of t. And then what do I do next? I plug in 4 and I plug in 0. And then I have this incredible function. But check this out. I can pop this in a calculator and get an answer because x prime is v. So let me write that down. And I know x sub 0. That's negative 2. So check this out. I know that, and I can calculate this on the calculator. I can solve for x sub 4 now. So my answer, the position at 4, is going to be, well, I'm going to move that to the other side. So I'm going to add negative 2 to the other side. Well, actually, let me start with this. Okay. Whoa. I'm going to start with this general form right here. I'm going to add that to the other side, and you get this. The position of 4 is the position of 0 plus the integral from 0 to 4 of x prime of t dt. Now here's what's huge. When I integrate x prime of t dt, the area under the curve of x prime, that gives me the distance traveled. This gives me the change in x according to the fundamental theorem. The change in x is the change in position. So this tells me the change in position of the function. So if I knew where it started and how much the position changed, that will give me the final position. This is fundamental theorem of calculus. Therefore, the application for this is x of 4 is x sub 0, the starting position I should know is -2, 0 to 4 of v of t dt. I know v of t. I pop that in my calculator, and I get an answer. Okay? So you would just do that in your calculator, and you would get some answer. And I'm not going to do that right now, but this is huge. Make sure this is making sense. It all connects back to this. The integral of v of t, which is v prime, or x prime, excuse me, is change in x. Final minus beginning. So integrating v tells me change of position. That's displacement. So if I get the final position minus the initial position. So make sure this is sinking in, that you process through this, because this happens all the time on the AP test. You're going to have a ton of questions on the Chapter 5 test that relate to this, a ton of them. Okay? So that's that one. Man, I have 2 more. This is a long video. Man, it's going to be long, but this is huge. Okay, the temperature of water in a tub at time t is modeled by the strictly increasing. So we know it's increasing. We know the first and second derivative exist everywhere. And it's measured in degrees Fahrenheit. And T is in minutes. Ooh, that's bad. W is measured in degrees Fahrenheit. And T is measured in minutes. Okay, at times T equals 0, the temperature of the water is 55. Okay, temperature of water is W. So the temperature at 0 is 55 degrees Fahrenheit. They tell you that. The water is heated for 30 minutes, and the values of W of T, so the temperature of the water, is given for various times. Okay, let's look at part A. Use the data in the table to estimate W prime of 20, the derivative. What's the derivative at 12? This is a super common question. 12 is somewhere between here. So if you were to graph these points, I don't know, you get some kind of a function. Well, the derivative at 12 is the slope at 12. And we've done this before. How do you estimate that slope? You take 2 points around it. You find the slope of the secant line to approximate the slope of the tangent line. So part A, you would say W prime of 12 is approximately, and we're going to find the slope between the 2 points around it. So it's going to be W at 15 minus W at 9 over 15 minus 9, which is 67.9 minus 61.8 over 15 minus 9. The units of W are degrees Fahrenheit, and the units of T are minutes, and that is the correct units. Now, interpret the meaning of this. Well, the derivative is, and this is going to be a positive number. 67 minus 61 is positive. So our derivative is positive. What does this mean? It means W is increasing, right? So interpreting this, the temperature of the water is increasing at this rate degrees per minute. So whatever this number comes out to be, it's increasing at this rate degrees Fahrenheit per minute, and that would be A. But here's B. Let's look at B. This is the big one. 0 to 20, W prime of T dt. Well, this is fundamental theorem of calculus. What does it say to do? First step, find the antiderivative of that, which is w of t. Then you plug in 20, which is w of 20, and you plug in 0, which is w of 0, and what do you get? 71 minus 55. So what's that, 16, I think? 16 degrees Fahrenheit. So check this out. This is huge. You integrate w prime, and it gives you change in w, change in temperature, change in temperature. So using correct units, interpret the meaning of this integral. So this integral gives you the change in temperature. Fundamental theorem. So you integrate w prime, it gives you the change in w. So you would say, what does this tell you? The temperature of the water in the tub increased by 16 degrees Fahrenheit from time t equals 0 to t20. That's what it would be. The integral of w prime gives you change in w, which is change in the temperature. And since it's positive 16, the temperature of the water increased by 16 degrees. So this is fundamental theorem, making all these connections. We got one more to do, and I'll probably warn you, you might want to split this video up into a couple. So Ben rides a unicycle back and forth, east and west, left and right. The twice differentiable function b models Ben's position. So b is the position function. Let's see, in meters. So the units is meters, and it tells you that there. T is in seconds. They tell you that there. So the table gives values for b of t, Ben, and Ben's velocity, v of t. So v of t is Ben's velocity. Use the data table to approximate Ben's acceleration at 5 seconds. So acceleration is the derivative of velocity. So they want the derivative of the velocity. We'll do this again. This is a very common thing. So they want to approximate the acceleration at 5, which is v prime at 5, right? Well, 5 seconds is in between these two. So if you plot these points, you'll get some curve from 0 to 10, but the derivative of v is the slope of the tangent line. You will use the slope of the secant line, right? So this is the same problem as we did on the previous one. This will be v of 10 minus v of 0 over 10 minus 0. From the table, it'll be 2.3 minus 2 over 10, which is 0.3 over 10, which is 0.03 meters per second squared. So that is part A. And why is it meters per second squared? Because velocity is meters per second. Time is seconds. So meters per second divided by second is meters per second squared. All right, part B. Huge. What is this telling you? So this takes any negative velocity and makes it positive. So all your velocities are positive. Now when you integrate velocity, it's the change in position, because velocity is x prime of t. If you integrate x prime, it gives you the change in x. It's x of 60 minus x of 0, change in x. So if this gives you change in x, it's change in position, right? And it's net area, but when you absolute value, all your velocities are positive. So if you had this would be distance right, distance left. If you integrate it, it's this plus this minus that. And it's your displacement, not your total distance. But when we absolute value, all of a sudden, this is on top, and you're adding all that, so it becomes total distance traveled. So I'm not going to, just because this video is getting really long, but they want left Riemann sums to approximate this. Actually, we can do this. With subintervals according to the data in the table. So we're going to have 4 subintervals. 3 subintervals. There's 3. So we're going to do left Riemann sums. So I'll go ahead and do this. This is approximately equal to, so what's the left side of these two? 0. So it's going to be v of 0, and the width from here to here is 10, so it's times 10. And here's our next interval. The left side's 10, so that's going to be v of 10, and the width is going to be 30. And these are all absolute value, by the way. And the last interval is from 40 to 60, but what's the left of these? The left is 40. We're doing left-hand Riemann, so it's going to be absolute value of v of 40, and the width from 40 to 60 is 20, so that's going to be times 20. And all these velocities are already positive already. So this is going to be 2 times 10 plus 2.3 times 30 plus 2.5 times 20. That's my answer for B. Now, using correct units, interpret the meaning. So you would say the total distance traveled by Ben on his bicycle from 0 to 60 minutes or 60 seconds is this many, and the unit's going to be meters, because velocity is meters per second. You're multiplying by time, which is seconds, so you're going to get meters. Remember, integration, you're multiplying velocity times time and adding them all up. You're summing them. Okay? And part C, just because I'm tired and you're probably tired, this is actually going to be a mean value theorem from chapter 4, because you're going to be guaranteed that the derivative, I think it's mean value theorem, I'm pretty sure it is, you're going to show that the derivative of the position from 40 to 60, if you find the slope of that, I believe it's going to come out to be 2. And if that's 2, the slope of the secant line, then you're guaranteed that the derivative of that will equal 2, and that's what they're doing, derivative, positions, velocity. So that's what you do is C. That's the end of this long video. Bye-bye.